Good evening, everyone. Am I audible? Can you all hear me? Okay. So welcome to this seminar from Center for Data Science and AI. Today we have with us Professor R.P. Singh, who's a faculty member in Atomic, Molecular and Optical Physics Division at Physical Research Laboratory, Ahmedabad. His research areas include light scattering, phase singularities of light, nonlinear optics, quantum optics, and quantum information. Presently, he is engaged in experiments on high-dimensional entangled states, free space quantum communication, satellite-based quantum key distribution, and quantum radar. The topic today is quantum key distribution, a paradigm shift in secure communication. I welcome Professor R.P. Singh over here on the dais to please take the talk forward.
Thank you, Ankur. Thank you for the invitation and the introduction. You have given me a chance to talk to audience, which is very different from the audience we face regular basis in conferences and classes. So thank you very much for giving this unique opportunity to talk to you guys. So before I go to the main topic, let me tell you that we are at the cusp of quantum revolution, and it's called Quantum 2.0. And why Quantum 2.0? Because we are already reaping benefits of Quantum 1.0. And Quantum 1.0, there you can say lasers, transistors, computer chips. They also use quantum mechanical principles. But Quantum 2.0, we are using the properties of quantum mechanics, which is exclusive to the quantum mechanics or quantum system. You can't find analog in the classical system. So that's the beauty of Quantum 2.0, and we can't stop it. It's going to come there, okay? And we have to be ready for that. So in this Quantum 2.0, or present day quantum technology we call, there are four verticals. One is quantum computing, another is quantum computing and simulation, you can say, and another quantum communication. Then you have quantum sensing and metrology, and fourth, you have quantum materials and devices. So these are four verticals. And let me go back to quantum computing, because this quantum key distribution or quantum communication or secure communication that came in response to or consequent to quantum computing. Why quantum computing? In 1994, Peter Shor in US, he gave an algorithm, developed an algorithm, which if you run it on quantum computer or computer that uses quantum mechanical principles, works on quantum mechanical principles, you can factorize large numbers, prime factorization of large numbers. And our present day encryption or that we use in day-to-day transaction over internet, all financial transaction, all the secure communication which we do present day encryption, that uses this prime factorization for encryption. And is this algorithm which Peter Shor developed, if you use quantum computer, you can break that problem, you can crack. So all the security is gone. Okay, once you have quantum computer, and you can run that algorithm, that prime factorization. So people said they got scared, all the securities agencies, they got scared. And you will hear stories that even FBI people started following the conferences on quantum computing. Okay, they were sitting there. What's going on? Let's know. So people got scared, and so in response to that, this quantum communication came. So because quantum computer uses quantum mechanical principles, so if you use communication using quantum mechanical principles, you can secure communication against quantum computer. So even quantum computers cannot break that encryption, or it will become secure even against quantum computer. So you have to use quantum mechanical principle to secure communication if you have threat from quantum computer. So that is the that from there it comes secure communication or quantum communication. That's the background because of quantum computer and this algorithm, and that made a lot of change. So we are having this quantum science and technology program, and we are covering almost all the verticals in all these labs. These activities are going on at PRL, and we are covering all the verticals as I told you. So let me go. How to enter or how to go next? School. Okay, fine. Thank you. Thanks. So quantum communication, we are saying, as I told, this quantum 2.0, it uses quantum mechanical principles or quantum systems or quantum states. So you have to like communicate using quantum states, and you have to use properties which are not there in classical systems. And so we have to have qubits. Instead of bits 0 and 1, we have to have qubits, and qubits are superposition of bits. Okay, you can say they are superposition of bits are. So let me write. So you can say like superposition of. So that's the thing. So if you write like this, I think it's coming. Yeah. So this is superposition of 0 and 1. Instead of 0 or 1, it's a superposition of 0 and 1. So that's what qubit is. And it follows laws of quantum mechanics. Instead of qubit, you can use qubit also. You can have another thing, 2 or q quart, and you can keep on increasing. So you can have number of states, you can call it. So, but most of the time you are using qubits in most of the problems. So that's what it is. So you use qubits, and so it provides unconditional security by using these principles, as I told, this no cloning theorem. In quantum mechanics, there is no cloning theorem. If you're using quantum states, you can't clone them. You can't make a copy of them. That's the beauty of quantum mechanics. There is like physical principle in quantum mechanics. And another property is if you measure the state, yeah, it interacts with some system, it changes. So somebody, some eavesdropper, suppose you are communicating through quantum state, using quantum state, somebody wants to measure, some eavesdropper or hacker wants to measure or interact with some instrument, it will change the state. Okay. And then we are using superposition principles, entanglement, all those properties of quantum mechanics to make our communication secure. So we will see how we make our communication secure, and how it is different from day-to-day present-day classical communication. In present-day classical communication, we don't have any limit on like error. Anybody can hack the line, or you can tap the line. You can tap the line, all those things are coming, you can tap the message and all. So it's not secure. But here, if you try to tap the line or the communication, you will come to know, and you can, it will introduce error. Okay, that's what I'm saying. If you measure the quantum state, it will change, or you can't copy. That's what you are doing. When you are measuring, you are copying somewhere. So it will change. You can't copy exactly, and you will introduce error. And immediately you will know, and then you will stop the communication. So that's the beauty. You can set a limit. If error is beyond that, I will stop the communication. Error may be there, it's a practical system, there may be error. Okay, it's not foolproof completely. So information, theoretically it's secure completely, but when you implement experimentally, there will be practical limitations. Okay, like detector. Suppose you are using some detector and you say 100% efficiency. It's not 100% efficient, anything. But theoretically, you assume that it's 100%. Same way, you are using, suppose, single photon source. At a time, only one photon. But sometimes source may have 2 photons at a time, or 3 photons at a time. So all those practical problems are there. So because of that, there will be certain errors. But you can put a threshold. Beyond this error, because of this practical limitations, if error is up to this, you can tolerate. And beyond that is come means because of some eavesdropper or hacker is there, and I will stop the communication. And that facility is not there in classical communication. Anybody can tap and you can't notice. Without being noticed, you can tap the line and you can have information. So that is the major like advantage when you are using this quantum communication. You can interrupt me in between. You can ask. I may not be very clear. Let me tell you, I'm Pakka Desi. Pura India education. Okay. So I'm not very good in English. I can't make stories, very nice stories in English. Okay. So you can ask in between if you are not following. Okay. Don't mind.
said communication has to happen in some kind. There has to be some quantum encryption algorithm. Only that could survive an attack from a quantum.
So I will tell you how. You make keys. How you secure your communication? Basically, your keys should be secure. Encryption, you have to encrypt using keys. So you have to secure your keys when you are distributing the keys. That's how you secure.
Right. So
when we distribute the key, okay, we are saying communication. When you're distributing the key, we are using quantum state in distributing the keys.
I see.
Okay.
But the one you distribute is generally the public key, right? The private key you generally keep it only with yourself.
So it's like a public. It is symmetric key distribution. So both the parties, if there are two parties, both will have same key. So it's symmetric key distribution, unlike asymmetric key distribution and all. So it's symmetric key distribution.
Thank you.
Okay, both will have same keys, both the parties, and they can encrypt their message. And key should be having same length as the message. That's the beauty. And one-time pad you have to make it secure. So one-time pad you have to use. That algorithm you have to use. So what is the threat? As I told you, very important to note that one can intercept now and decrypt later. Suppose you are not developing this technology and somebody is tapping your line and they can store all the information, and the moment they have quantum computers without telling, maybe China may have already developed, you don't know how much public they are telling, or USA might be having better quantum computer. So they can have all the information and they can decrypt it later. Okay, maybe after 10 years. So defense records are kept for 30 years or 40 years. Then Canada health records are maintained for 90 years. I was reading. So some records data are kept for a long time, and if somebody is like tapping us, and then they can decrypt it later. So it's very important. So one has to develop this technology, and one has to secure communication. Okay, using this quantum key distribution. An existing optical link cannot be automatically assumed. You can say we have communication, we have lines, fibers, and all. Whether we can use this quantum state to for using these fibers. Whether we can have this quantum communication using these fibers, existing infrastructure. So using existing infrastructure, you can't use this quantum key distribution because there are optical amplifiers. As I told, you can't do cloning. So optical amplifiers, it amplifies, clones, copies. That's how you amplify. So you can't use these things. So existing infrastructure, which is there for optical communication, fiber-based communication, you can't use. You have to have some new infrastructure you have to develop. Okay, you have to use dark fiber, and then you have to put at the nodes new infrastructure, new devices, so that you can have quantum key distribution. So how you go about this quantum communication? You require single photon source or source of entangled photons. So what is single photon source? Means there is a source where one photon is coming at a time. Okay. When we say photon, it's a quantum mechanical system. Okay, single photon. When you say single photon, it's a quantum mechanical system. When you say electromagnetic wave, it's classical electromagnetic field. You can explain Maxwell principles. So single photon source means one photon is coming at a time, or you have to use entangled photon. So one photon you can write you use some variable, as I told. Example of superposition I didn't tell you. Suppose you have a coin. Okay, it has head and tail. When coin you toss and it's rolling in the air, so then you can't say whether it is head or tail. So it's in the superposition state when it is in the air, when it's rolling. And then suppose you say head and tail, and you associate some probability here, C1, and amplitude, you say complex number. So it is called amplitude, complex amplitude you associate, and mod of C1 square plus C2 square. Suppose they are in two states only in that system, that should be 1. Okay. So that's the beauty, this complex amplitude. Okay. That's the superposition state if you are talking. This amplitude, this C1, C2 has to be complex. So that kind of state, suppose, is there, you call superposition. And entangled state is extension of superposition. Suppose you have two such systems, two coins. Okay, I toss one coin here, if head, and one coin here. So suppose here it is head, and by some link, if head is here, here also head is coming, and you can take it far apart, kilometers apart. Head is coming and head is coming here also. Here tail is coming here also. So that kind of state, suppose I say C1 head plus C2 tail. So that kind of state is entangled state. Okay, so it's a correlation, very strong correlation, which you don't find in a classical system. If head is here, okay, here also it may be far apart, kilometers apart, it will be head. Okay, if it is entangled, it's a quantum, it's a system you can't find in classical system, that kind of analog. So this entangled, so you can have two photons which may be entangled, and you can use some of the variables like polarization. If you have this very light, polarization is there, so photon also will have polarization. You can have momentum, you can have orbital momentum, you can have a time being. There are many variables we can use, and in that variable it has to be entangled. Like coin, I have associated head and tail. So similarly, you can have associate many variable to a physical system, that is photon. You can take electron, then you can take a spin. So depending on system what we are taking, suppose you are taking atom, if you have, like, you might be having science background, some of you. So atom, there may be energy levels, you can take energy levels, discrete energy levels. So depending on system what you are considering, you can have like this kind of states. So you can form like superposition state or entangled state, and you can use them for quantum communication.
I have a question.
Yeah, sure.
So when you are saying that they can be entangled in momentum or energy levels or something like that, so can we control these things ourselves, that where does the entanglement exist, or are they entangled in all the variables like momentum, energy, and everything?
In quantum
it
mechanics, it's like measurement, what you are measuring. Unless until you measure, you can't say anything, because measurement changes. So whatever variable you are measuring, it's entangled in that only. You don't know, you can't say anything about other variable as long as you are not measuring. So when the variable you are measuring, it is entangled in that only, because you are measuring.
I see.
So for other variables, you can't say unless until you measure. So the variable you are measuring, it is entangled in that.
But do we know that in advance, that
advance you can't say? In quantum mechanics, in advance you can't say unless until you.
Right. Okay.
So that's the beauty. Like I use it's superposition state. You don't know whether it's horizontal or vertical, or head or tail, horizontal polarization or vertical polarization for a photon, unless until you measure.
All right, but can in advance we decide that we will be measuring momentum, or will be measuring energy, and then we figure out that, okay, they are entangled in momentum or they are entangled in energy, and then go for one of it?
Certainly, when you are going for experiment, you have to set up your apparatus, detectors and all, and you have to decide which kind of entanglement you want to study for your problem. Okay, they have a lot of applications. So when you are seeing photon, because photons, they are flying qubit, you can send from one place to other place. That's why they are used for quantum communication or quantum key distribution. Okay, so there we study polarization. So you have to decide, and accordingly you have to set up your apparatus. Then accordingly you set up detectors, like photon detectors, single photon detectors you have to make. You have to assemble, and polarizers are linear polarizers, quarter wave plates, half wave plates. I have not made that setup because that will be slightly more specialized, but you have to use accordingly. And then if you want to measure energy, suppose you are saying, then you have to have a spectrum analyzer and other things you have to. So depending on, yeah.
Can I simultaneously measure multiple properties?
Energy, momentum simultaneously? Like no, not simultaneously. You can't measure one at a time. One at a time. Like there is duality of entanglement. So you have to like distinguish in other variable. So you can say that other variable is entangled. Suppose at the same time it is entangled in OM, orbital momentum or momentum, and at the same time entangled in polarization. So there is duality of entanglement. You can't distinguish. So if you start in polarization for measuring entanglement in orbital momentum or momentum, you have to start out like you have to make it different in polarization. Then you can measure. So at the same time you can't measure both.
cryptography, the classical cryptography we use, like in that as well, we have certain type of relation in between two sending codes. So is this equal to that entangled photons?
So this entangled photons, basically you are developing key. That's why I'm saying key distribution. Key distribution is very important. Once, like how you encrypt the message, you have to distribute the key to the parties, okay, which are communicating. So if you can distribute key securely, so that no eavesdropper or hacker has information about your key, you can safely encrypt your message. That's the beauty. So for this key distribution, I'm making keys or distributing keys to the parties which are communicating. We are using quantum mechanics. That makes all the difference. There, when you're using normal cryptography, as I was telling, like based on RSA algorithm, AES and all those things, okay? So there you can, because it based on algorithm, hardness of algorithm, hardness of the problem. So if you have some algorithm, better algorithm which can break that, okay, or quantum computers or some new algorithm comes which can break that problem, okay, sort out that problem. So your encryption is gone. You can crack the encryption. That's what I was telling. You can keep on storing. The moment quantum computer comes, already algorithm is there. Peter-Source algorithm is there. You apply that, you can crack the encryption, that classical encryption, okay. But here you can't crack, because key are based on quantum mechanical principles. They are secure. So that's the difference between normal classical cryptography and quantum cryptography.
So continuing on that, and like, is it provably impossible that you cannot use just classical, maybe much more enhanced cryptography than what is being used?
So yeah, there are two kinds of cryptography. You are right, and a lot of debate is going on. One is called quantum safe cryptography. One is future safe cryptography. Okay. So quantum safe cryptography, they are coming out with algorithms which are tougher. Even quantum computer, it will be very tough. But it's on presumption that that will be tough. Okay. So quantum computer, suppose somebody like you, someday like 10 years down the lane, you get very nice computer and some very brilliant mind develops algorithm which can crack that, like is hardness of algorithm. Okay, it all depends on your like computing power and the brilliance of how you develop algorithm which can solve this problem. But here, when we say quantum key distribution, that is called future safe. So quantum safe, like you use algorithm which even quantum computers find difficult to break. Okay, but again, it's hardness of the problem for quantum computer now. Okay, it's not like that it can't be broken. But when you say quantum key distribution, that is future safe because it's using physical principles. Okay, it's not based on hardness of the problem, hardness of an algorithm. So that's why it always remains safe. Okay, you don't have to bother about quantum computer. Quantum computer may have like millions of qubits. Okay, very powerful quantum computers. You can come out with very nice algorithm. It doesn't matter. Okay, you can't break that because you're using quantum mechanical principles to safeguard your communication. That is a.
So hackers can't decode this.
Hackers, yeah, they can't hack it. So theoretically, they can't hack it. As I told, when you do the practical, when you go for practice, so your detector, suppose you are using detector, you are using photons, you have to detect photons finally, based on photons. So they may not be 100% efficient. You may miss few photons, okay? And then your fiber may have losses. So there are many practical limitations when you go. And that's why you put some error threshold there. All the like protocols, you say quantum key distribution protocols. So you have to define a threshold. If this much error is there, it's fine. I can take care of it through privacy amplification, error correction, and all those things. But beyond that, means there is third party, I should stop my communication. So that is the thing. So theoretically, it's secure, but experimental limitations are there, and to take care of that, you have to define a certain threshold, error threshold. What I. Mhm. Yeah, that's what. It's very, my son was asking same question. He is in law. Okay. So, okay, suppose terrorists are doing something. Okay. So how you are going to find out? So answer is that, like, you can't stop quantum revolution. Okay. Quantum computers are going to come maybe 5 years, 10 years down the lane. And you have to secure, okay, your communication. So you have to go for this technology. Okay. Quantum key distribution, you can't avoid. Like everything, there are two aspects. Okay, some like nuclear weapons, some rogue states can use, but then you have developed safeguards. Okay, similarly you can like you can have trusted nodes when you are saying this quantum communication. So suppose from one node to another node you are doing, so you can have trusted node, and you can decide like this is the authority or this is the joint parliamentary committee, opposition party is having is chairing that committee, and there are some experts, so they can look at the information at trusted node. Okay, so I will go when we talk of this trusted node and untrusted node, I will talk, so you will have some idea. So from trusted node you can have information. Okay, so but like this regimes, government also can use that data against opposition. So that's why I'm saying some mechanisms have to be decided. Like nuclear weapons, there are certain safeguards. Similarly, here also you can say some committees there and experts are there, and then they can check if there is some problem. Okay. So, but as technology improve, you will come out with the ways how to take care of that. But you can't avoid, you have to go for that. Okay. So that problem will come. Even terrorist organizations and criminal elements can use, and you can't track, like nowadays phone tracking is very good to track the criminal activity. So he was asking that, so you can't go for consumer like day-to-day market. So that's what he was asking. So initially this technology is for defense and strategic thing, financial and all those things. And gradually as it matures, this standardization happens, it will become like for everybody, available for everybody. So you are going to ask another question?
Yeah, because let's not think about that extreme terrorist organization or something, but just simply the cryptocurrencies, they are already threatening monetary policy authorities in many countries. If they start using this technology, then I don't know what the Reserve Bank is going to do.
They are not using this technology. They are not using QKD, okay, or they are not using quantum safe. Again, some algorithm they are using, which is better than like RSA or other AES and all those things. It's better than that, but it's not like quantum safe. So. So this quantum states, as I told you, are doing communication. I'm not running what time. So this, because you are sending your signal, as I say, photons. So you can use free space or fiber. Both you can use. You can have fiber communication. You can send your photons or quantum state to fiber or free space. So why these satellites are required are because fibers, when you are sending through fibers, they have certain limitations. They have inherent losses. So you can't go for very long distances. I told you this quantum states, you can't amplify, you can't make copy. Present day communication, optical communication, you put amplifiers. So when signal is getting weak, you amplify that. But when you are using this quantum states, you can't amplify them. Okay. So you are sending fiber through fibers, they will become weak and you can't amplify. So that is the problem. So using fibers, you can't go for long distances. So you have to use satellite if you want to go for long distances. So you can communicate through satellites. Like here it's Bangalore and Ahmedabad. So this is like, as he was asking, a trusted node and untrusted node. That's what it is shown here. So satellite here, this communication, we are using free space or satellite-based quantum communication, a quantum key distribution. So here satellite is acting as untrusted node. So here we are using entangled photons. When you are using entangled photons, so all your keys based on this property of entanglement property, okay? And because it's using this quantum mechanical property, and so this satellite can act as untrusted node. And suppose some other satellite, suppose it is trusted node, And so you are keeping data here, okay, your key here, and using RF signal, some other satellite, smart one, okay, they can take data from here. So if it is trusted, so here this is untrusted. Here you are just having entangled photon, and one of the entangled photon is coming here, another is going there, Bangalore, and then using you measure the polarization of these photons and you develop the key. So you have secure key in Ahmedabad and Bangalore. Okay. So this is untrusted node, but here there is another quantum key distribution protocol. This is called entangled photon based quantum key distribution protocol. This is another where you use a single photon source, okay, or weak coherent pulse. So you first establish key with station A. So station A is some ground station where you have telescope or some detector which can receive signal from the satellite, okay, which can measure photons at the ground station. We call optical ground stations because we're using optical signal. Photon is optical basically. So you have some ground distance, some telescope, and first you establish key Ka satellite. One K is here, K is here, same key, symmetric key. You are asking symmetric key. So we are establishing this symmetric key here, K and K with one station. Then we establish KB with another station B, KB, KB. So now satellite has both K and KB. Satellite does the XOR operation, encryption does satellite K and KB, and you send it to station A, and then you do the another this KB XOR operation. You get the key. Same way you can get the key here also. So you can have same key K and K at the A and B. So basically XOR operation. Many of you data science students, and you might be knowing better this all those gates and all those things, XOR operation and all those things. So that's how you get, this is trusted node. Okay. So here satellite is acting as a trusted node because here key is being kept in the satellite. Okay. Here you are not keeping the key in satellite. You are using entangled photons. It's coming to the station, but here key is in the satellite and somebody can take information. Okay. Using RF communication. So that's this is untrusted, this is trusted, and this is trusted. Same way you can have in the when you are doing like ground fiber thing. So you can have trusted node and untrusted node. Trusted node where you keep the key. Okay. So that's what I was telling some organization, you want to have key. Okay, you have key, somebody is doing, and from there you can have information. Okay, somebody doing mischief. So trusted node. So China is doing this thing only. They are developing thousands of kilometers of quantum communication network, quantum key distribution network using trusted node. Okay. So the most notable, so you can use the free space as well as fiber, as I told. Fiber has certain limitations. So you have to go for satellite-based quantum communication. And if you want to go for satellite, first you have to do free space because free space communication, like first step for going to satellite-based quantum communication. So Chinese scientists have already sent a quantum communication satellite. You must be reading in newspapers and all. That was Mischief. They called it Mischief. And why Chinese sent this satellite? This Snowden, you must have heard Snowden, 2013. He leaked papers like National Security Agency, USA. And Chinese realized that USA is taking a lot of data from China's activities. Okay, they have a lot of information. It's everything has not come to the press, but the media. But they realized that USA is doing like having a lot of information about Chinese activities, and they started pumping a lot of money in these quantum technologies. And they were the first country to send this quantum satellite to the space, and they established this quantum key distribution using satellite, as well as they are the leaders in now quantum technology. And all this quantum boom, or you can say quantum 2.0, this quantum revolution, that is because of China's leadership role. It came in response to Chinese investment in that area and Chinese achievement in this area. After this satellite went into space 2016, they have a quantum flagship in Europe, billions of dollars. Then National Quantum Initiative Act, USA, billions of dollars again. And many like private enterprises started investing. Government is giving like incentives to private investors. Okay, so a lot of activities started, and India also started like rather announced in 2020, like February, this budget thing, a national NMQT, National Mission on Quantum Technologies and Application. So they also allocated around $1 billion, 8,100 crore. Okay. But India being India, it is announced in February 2020, but still it has not been approved. It's on just paper. Okay. So still project has not been approved. It's 2022 and budget has gone. So I don't know when it will be approved. So that's, and they have plan of 2030. They have established, like Asia and Europe, China and Austria, they established quantum link. So they have planned to worldwide quantum communication network. They will be providing service to whoever is willing. Already Brazil and many other countries like BRICS countries, they are willing to take services from China. So there will be many countries willing to take services from China. So they have planned to set up this quantum key distribution network global by 2030. And all the countries like Europe is having European quantum communication infrastructure. So by 2027, they plan to have this quantum communication infrastructure all over Europe. And China is developing, already China has developed quantum key distribution network for 4 metropolitan cities. So that's what it is. So that's what it shows, Chinese achievement. You can see that 1,203 kilometers, they have distributed, here satellite is acting as untrusted node. They have distributed entangled photons and they have established key. So this is their setup. I will not get into detail of the setup. And this again, they have used satellite as a trusted node here. And they have used the single photon source or weak coherent pulses. And they have established this key. This is Austria in Europe, and this is a Chinese citizen, Jinglong, and 7,600 kilometers. And they had a video conference, okay, between Chinese Science Academy and Austrian Science Academy. And this is another Chinese session. Okay, so they have done all this. Okay, and then it's not only China, European countries also, Italy, Germany, they are into this free space quantum communication or satellite based. They're trying. This is Italy, result from Italy. So rather, they were the first to have published results in this field, 2015. But China has beaten all of them and gone ahead. And then you have Japan also. Japan also tried in somewhere 2017. Okay. So they also tried this satellite, very small satellite, very compact ground station. They also had this key distribution. But again, it was trusted, not untrusted. They were using weak coherent pulse. Okay. And then Germany also using rocket, this like aeroplane, 20 kilometers, and then ground station. And then they have done the feasibility study using satellite also. And Germany is the only country which has shown that it's possible to have quantum key distribution using geostationary satellite. Okay, that's the only country. Geostationary is quite much above 36,000 kilometers. So with 2-3 geostationary satellite, you can cover the whole globe. Okay, if you can do. But when you say LEO, China has done using low Earth orbit satellites. So you have to have number of low Earth orbits to cover the entire globe. So that's technicalities, but that's what Germany has done. But still, just feasibility study. They have not done like detailed key distribution. Singapore, very small country. They are also much ahead compared to us. Okay, they have spooky one, but they have not done quantum communication. They have just sent this quantum source, entangled photon source in space, and they have tested that their technology, this entangled photon source is working properly in space. That was 2019. And then they have plan of setting up ground stations and having quantum communication, quantum key distribution in 2024. They are going to have Spooky 2. So that's what. And Canada has also proposed, not it like they have not flown this mission. Satellite has not gone. So, and there are many international efforts. So when I say satellite based quantum communication, you can have uplink as well as downlink. Uplink means you can see that this is like here. Downlink, this is downlink. because beam is widening. So beam will have certain divergence as it propagates in space. So that's called divergence or diffraction. So this is the downlink, and then this is uplink. You see here, this is uplink. Okay, when here, this is uplink. Okay, so some countries are planning for uplink, some countries are planning for downlink. So China, this MISIUS, which has already been done, that was downlink, and downlink is easier. You get better signal to noise ratio. Uplink is much difficult, and it has certain advantage, but downlink is much better, and you get more signal to better signal to noise ratio, and you can have more key. So our strength at PRL, we have developed entangled photon and single photon sources at PRL. We can have very large number of entangled photons per second. That is very important because it will depend on how much key you are making per second. As I told, you have to have key length of same size as your masses if you want to make it secure one-time pad. So you have to have a large number of keys. So it's very important that you have large number of entangled photons to make like kilobits at least. kbps, like kilobits per second, to make that kind of key length. And entangled photons at communication wavelength, we say 1550 nanometer because it has least attenuation in fiber. If you are using some other wavelength, suppose 800 or 750 or something, so it will have very high attenuation in fiber. So our fiber, this communication fiber, they're designed for 1550 nanometer. And if you want to have this fiber based communication, you have to use 1550 nanometer. So we can make that kind of entangled photon source, which is at 1550. Then you can have hybrid entangled photon. You can use different degrees of freedom. Like I was taking polarization only most of the time, horizontal, vertical, but you can use other variables, combine like orbital angular momentum or some other variable. You can combine time being or path entanglement. So you can combine along with polarization some other variable. Okay, and you can have hybrid entangled. That will that has certain advantage when you are doing this communication. It makes more robust your communication. Then you can have non-separable states of light, and you can use for some protocols, quantum information protocols, which don't require non-locality. I will not go into this non-locality and all. That is too like complicated topic. So challenges on the way to quantum communication, a single photon source, I was telling, still there is no like deterministic single photon source, a deterministic entangled photon source. So a struggle is going on to produce a deterministic single photon source and deterministic entangled photon source. And it has to be compact, okay, chip based and bright, like a good number of entangled photons you should get per second. And so effort is going on in this direction. Okay, deterministic and true single photon source, as well as larger number of photons per second pairs. And then photon number discriminating detectors, that is very important. Your detector, present detectors, it can't distinguish whether you are getting just one photon or two photons or three photons. So that is very important if you want to implement some quantum information protocols, so that you can discriminate whether you are getting one photon or two photon or three photon. And as I told, repeated again and again, efficient single photon detectors, you have to always increase the efficiency of your detectors. Okay, it's better. So making it foolproof your communication. Larger aperture low noise detector, so that you can have more signal and low noise. So that is important. And compact detection system, present day detection system, what we are using, it's quite, it takes a lot of space, but nowadays people are trying to have everything on chip. So it will gradually, they are reducing the size of this setup. So a memory, it's very important to store the quantum states. Suppose you want to have this quantum computation, or you want to take, suppose through fiber, you want to take your quantum state, a quantum key from one place to another place, longer place. So you have to have this memory, and where you can store, and then you can take from there. So quantum memory is very important. That is still it's a research stage, and there is no commercial this kind of device, quantum memory, and it's very important component for quantum computing as well as quantum communication, fiber based basically. So what are the expectation? Integrating free space quantum communication with fiber based, that's very important. You can't have fiber only, you can't have free space. So you have to have both. Okay, like city you want to do, you have to have fiber, and if long distances, you have to do the free space, satellite based. And certification of QKD devices, that is security analysis against different kind of attacks. As I told, there are certain loopholes, and eavesdropper can use these loopholes or these defects in your setup and extract some information about your key. So you have to have certification for QKD devices, quantum key distribution devices. They are secure, what you are claiming for. And you have to have ground stations if you want to have satellite-based quantum communication. Then free space communication at telecom wavelength, so that you can relay your whatever you are getting through free space. Suppose it is at communication wavelength 50-50, you can directly send it through fiber. But suppose you are using 810 that China has done. They have done this missile satellite 810 nanometer. So again, you have to use the ground stations where you are receiving the key, that you have to use a trusted node, and then you do some XOR and all those things, and you relay through fiber. So it's important to have free space communication telecom wavelength. But telecom wavelength, we don't have very good detectors, okay? And if they are there, they are very costly at present date. They are very costly. So that is the problem. And human resource development is certainly very important. Not many people are there who understand this kind of things. So long-term quantum communication network integrating entanglement-based QKD with QKD using weak coherent pulses. As I told, you can use weak coherent pulses. Weak coherent pulse means on an average, you have pulse laser. You can have CW laser like this pointer. If you have pointer like it's CW, okay. But you can have pulse laser also, like nanosecond pulse, and you may have megahertz, like 10⁶ pulses per second. So that's called pulse laser. So suppose you reduce the intensity of laser in such a way that per pulse less than 1 photon is there. So you can approximate as a single photon source, but it's still not single photon source, true sense, just approximation, because you are reducing the intensity, okay. So it's not true single photon source, it's approximation to single photon source. Better to call it weak coherent pulse, because you have reduced the intensity of the laser, so that per pulse on average per pulse you have just 1 photon or less than 1 photon. So both you can use, and there should be way to integrate both the techniques. And integration of quantum communication network with the classical communication network. Why I'm saying because you have to integrate, because when you're using entangled based QKD, you can't have very large number of keys, okay, because there are limitations. You can't present the limitation. I don't know when it will be broken. You 10⁶, now we are stuck at, you can't have like 10⁶ photon pairs per second when we are using entanglement, okay. And when you're using this weak coherent pulse, you can go up to gigahertz, okay, 10⁹ or so. So for day-to-day activity, suppose you want to do encryption, then you have to go for this weak coherent pulse, and you want to have more secure, then you have to go for entanglement based. So, and there should be way to integrate them. Integration of quantum communication network with classical communication network, that is very important. There are techniques they are following, how with some extra gadget, if you put that in these nodes which are involved in classical communication, how you can upgrade that, some using dark fibers and some extra gadgets at the nodes. Then quantum memories for quantum communication network towards distributed quantum computing, okay. And task ahead for India, verifying existing free space quantum communication protocols and developing new, more efficient, secure, and less resource intensive protocols. That's what India has to do, and we are working in that direction. Developing at least 2 optical ground stations for quantum communication to transmit and receive quantum states of light, as China has done and other countries are planning. So still we don't have like optical ground stations, steady ground stations which can receive information or receive the signal from satellite. They are not still ready. We are working on it, but still they are not ready. It may take time, 2 to 3 years. And development and demonstration of free space quantum communication and cryptography using satellites. Okay, that's what the ultimate aim, satellite-based quantum communication. And what we have done here in PRL, we have implemented quantum key distribution protocol in free space for 200 meters as well as 300 meters using weak coherent pulses, as I explained you what is weak coherent pulse, as well as with entangled photons, means you can have trusted as well as untrusted node. And we have got a good number of like good length of key, 3.5 kilobits per second. And here weak coherent pulse, as I told, you get larger number of keys. So 150 kilobits per second, that's what we have achieved. And you see this Q bar is quite quantum bit error rate or quantum bit error ratio. It's less than 3%. Threshold is 11% for this protocol, the protocol which we have used, BB84 and BBM92. Threshold is 11%. So our error is quite less than 11%. So it's secure. Okay. So here again, it's less than 11%, 5%. So this is the setup. You can see here. This is like transmitter, and here we have mirror, and it reflects. So we are covering 200 meters. So this transmitter and receiver, and that's how we have distributed photons, and we have developed key. This is a schematic for entangled photon source. Okay. We have developed entangled photon source at 810 nanometer optical wavelength. We have to have 1550 also. It's not shown, but we can develop that. Okay, we have. So future plan for work at quantum science technology program at PRL, effect of turbulence, and how to mitigate it for terrestrial communication. So if you are going for satellite, you have to have see the effect of turbulence and all those things. And simulating conditions for uplink and downlink, which is better, whether really downlink is better or uplink is better, one has to check. Okay, and one has to do experiment as experimental simulation, and that we can do, and we are planning to do. Development of device independent quantum key distribution protocol. As I was telling, I'm telling again and again, device may have some loopholes. So there are protocols which are device independent. Of course, you get a less number of keys, but there are protocols which are device independent. So one has to develop device independent protocols, and in such a way that you get a good number of keys also using device independent protocols. And entanglement swapping, you have to do entanglement swapping and quantum teleportation if you want to have like long distance quantum key distribution at the ground. And one can use a structured light for we work in structured light beams, vertex beam. I will not go into details, but one can have different shapes of light, spatial modes, and Gaussian cell model beams. There are so many structured beams, and that will provide robustness to key distribution against this turbulence and other atmospheric disturbances. Development of photonic quantum computing, since it is the best bet for quantum internet. Quantum computing, I didn't go into much detail, but there are many platforms like quantum computing is happening. You are using superconducting circuits, superconductor based quantum computing, and then you have ion based quantum computing. You have photon based photonic quantum computing. Okay, so there are different platforms like silicon spin based quantum computing. There are many candidates for quantum computing. Nitrogen vacation centers based quantum computing. There are so many candidates. So one doesn't know which one will finally have say which one will succeed, or which one can be scaled better and will be easy to scale. So this photonic quantum computing is also very strong candidate for quantum computer. And how things move with government of India, just I will finish with that. So it started in PRL with a project presentation, okay, including budget and timeline given by me to principal scientific advisor. 2015 itself, we gave this full budget and everything for satellite-based quantum communication. That time, this Chinese satellite has not gone. And I was called around after a few months, I was called to Space Application Center Ahmedabad to discuss that project. In the meantime, I pursued this with Department of Science and Technology. We got certain funds for this 200-meter quantum key distribution. And then we keep on pursuing with ISRO, and we sent it to ISRO 2018, full proposal. Finally, we like standing project approval committee. Any project beyond 25 crore, it has to be approved by standing project approval committee. So we submitted to that also. Okay, that was in January 2019. And so in the meantime, we kept on working. Okay, and in consultancy ISRO headquarters, we finalized 23rd September 2019 for SPAC. Everything was complete, but still project is like not sanctioned officially. So you can see 15 I am trying, and it's 22. Still there is no official sanction for the project. And the very funny part. ISRO headquarters gives us timeline to deliver the payload without sanctioning the project and the budget. So that's how this government machinery works. They have not officially sanctioned the project. They have not given any money for the project. Then say, you give the payload, we'll fly. So that's how these government agencies work. So you can see 15 I'm trying, it's 22, still it's not officially sanctioned project, and that's how the government machinery works. So we need to promote startup companies and not-for-profit research centers. They are models in Europe and USA owned by working academics and research scientists. And my student Praveen, who has done PhD with me at PRL and had extensive postdoctoral experience in USA, Germany, Canada. Now he has started a company, okay, incorporated. So still it has to be recognized as a startup. So you can go to the website and see. So, and that's what it is. And we are mentoring this. He's our student, so we have to mentor him. So let's see how it goes. So that's what it is. Thank you. I have taken too much time. I was supposed to finish in anyway.